So today we're going to learn about thermodynamics and heat engines. And so I'm going to walk you through this, and then you can go ahead and afterward you can watch some of the longer videos. I'm going to show you some video clips, but I'm only going to show you some short video clips, and I'm not going to show you the full gamut of all the video clips. So here I go. I'll be right there. And this first one actually is this is kind of a theme through this, is that I found this old school video clips that you may have seen if you were a high school student back in the day, before I was in high school, maybe when my dad was in high school. Anyways, they're really simple animations of a lot of different types of engines that we study. And so I'm going to show you a couple short clips, 1 minute or 2 minute clips of these, and just talk about them a little bit. This first one is about thermodynamics in general. So let's just begin with that.
The blacksmith's forge is a furnace for heating metals so that they can be worked. If we could magnify this piece of red-hot iron much more than is possible with even the most powerful microscope to thousands upon thousands of times its actual size, we would see its individual molecules darting back and forth at tremendous speeds, far greater than in this animated representation. We do not know what these molecules look like, but according to the kinetic theory of matter, we may visualize the molecules as perfectly elastic spheres. As the iron cools, the speed of the particles or molecules diminishes. In fact, temperature is a measure of this speed.
So we have a situation here where this is showing us that the heat is causing the molecules to move up, and we're going to use this directly to show you how heat engines work. So in this next situation, it's talking about basically the basic idea of combustion.
When air is forced up through the hot coals of the forge, the oxygen of the air unites with the carbon of the coal. In this chemical reaction, heat is given off. It makes no difference whether the carbon is present in the form of coal, wood, oil, or gasoline.
And we're going to find out we can even use things like nuclear for heat as well. So anyways, just a couple of quick little things to show what's going on. So here we have some definitions for the first law of thermodynamics, and just to kind of like see what's going on here, in the notes on the right it says heat, and heat is the addition of the a letter Q. It's not H, it's Q. And so this is like a fire going underneath, and this is a piston. And you can see that the drawing is showing the molecules moving slowly in a small letter U. U, as you hopefully know, is the letter for the internal energy of the molecules inside. And so this is showing that if you add Q, it is going to cause an increase in internal energy. So this says adding heat can cause an increase in internal energy. And so also, taking away heat can cause a decrease in internal energy. And I'm going to show you that in this video right here. Same thing, if you press down on the piston, work is being done on the system. That's how we say it. And when work is done on a system, then that causes an increase in internal energy. And then vice versa, when you have work done by a system, that means the piston pushes up, then that will cause a decrease in the internal energy, and the internal energy is the molecules on the inside. So we can kind of take a look at a couple of these things by looking at this activity from PHET. So in this thing for PHET, we're going to explore the ideal gas laws here. And what I'm going to do is I'm going to take the pump, and I'm going to pump up some gas inside, and you can see I have a temperature here and a pressure here. I am going to put in some light particles as well. Here's my light particles, and I'm going to pump some light particles in as well. And you can see my pressure is at 23 atmospheres. My temperature is at 300 Kelvin. You got to remember 273 Kelvin is uh, ice freezing, and so 300 Kelvin is right about room temperature. Okay, and so what I'm going to do now is I'm going to put some fire on there, and you'll see that as I do that, the molecules will begin to move faster, and the pressure will increase, and the temperature will increase. And you see the pressure is going on up. I'm going to add some more molecules to the mix just to see if I can get it going a little more. If I cool it down, the molecules begin to slow down, and the temperature will also drop, and the pressure will also drop. So there's a relationship between the internal energy. The internal energy would be the letter U on the inside here, and then Q would be me causing the Q to go to add heat to the system. And let's see if we can get this thing to overheat. And I also can do work to the system, and this is what doing work to the system. I grab this little handle and I press in, and I pop the lid off. So that caused way too much internal pressure, and it just pops the lid off. And so that's the idea. Okay, so now we're getting into the first law of thermodynamics. And the first law of thermodynamics, I'm going to show you a what's called a heat engine, and an actual heat engine. It's a steam engine, and so it's only 4 seconds. I'll show you a lot more than that in class. But so here's the 4 seconds of this, and it's just basically this is the steam engine is exactly what is detailed here. And so inside of this little house is a firebox, and I have some fuel, and the fuel is burning underneath this water tank. That water tank has a little tube, which you can see on the side right here, and that little tube goes into this little engine, which is a cylinder. And that cylinder, the steam will come out this side, but it pushes the cylinder back and forth, which makes the wheel turn. And so you can see the little piston going back and forth there. And that's an actual apparatus that we will see in class. So what this is a drawing here of the first law of thermodynamics. And so the first law of thermodynamics is similar to the law of conservation of energy. So before we said that gravitational potential energy could be turned into kinetic energy, and the kinetic energy is related to the amount of work that we do with the work that can be done. So the same way here, the potential energy is the fuel that we will use to burn the fire. And so we'll burn this fire. That fire will change the kinetic energy of the molecules on the inside, which are water molecules, to make them go all fast. And so the molecules inside have a lot of speed, which leads to pressure. And that pressure is going to travel through this tube and push on a piston. And when that piston turns the wheel, it allows us to do work. And so the first law of thermodynamics is basically a restatement of the law of conservation of energy with respect to heat energy. It basically states that we can follow energy as it changes from one form to another. In the heat engine examples, we add heat, which is Q, to a system, which raises its internal energy, which is U, and this allows us to do useful work, W. So that's the first law of thermodynamics with respect to heat and conservation of heat energy. And then we have the second law of thermodynamics. And so here I have another engine, but this is a steam turbine. In a steam turbine, instead of having a piston that goes back and forth, it actually spins. And so the heat will do the same things before. It will heat up water. The water will turn to steam. That steam will create pressure. The pressure will go into, in this case, not a cylinder with a piston, but it'll go into a turbine. And these white parts of the turbine actually are free spinning. And the pressure causes them to spin. And they spin pretty fast, actually. The steam comes out and allows us to turn something to make it to spin. So the question here for the second law has to do with the heat flow. Energy always goes from high to low. And since it always goes from high to low, we can employ this idea where we have a high temperature going in and then a low temperature going out into the atmosphere. And so the heat wants to escape. And because it wants to escape under this high pressure, we can say that we can make it do work for us. And so the work that we can do will always be equal to the difference between the high heat side and the low heat side. The high heat side being the fuel and the low heat side being the ambient temperature. So the second law of thermodynamics refers to the direction of heat flow. On average, heat always flows from hot to cold. This means that the hot air or water vapor or gas will expand outward to a colder surrounding area. This also means that we can make a machine to harness this energy and do useful work. QH is the source of heat energy as is applied to the system. It could be wood, coal, gas, nuclear, anything that applies heat. QL is the sink, which is the low temperature end that is surrounding the engine. It usually is ambient energy, ambient temperature, which means it's just going out into the room or out into space. That's ambient temperature. W is the work that we can get out of the engine, which depends on the equation W equals QH minus QL. Okay, so now we have some heat engine diagrams, which, can I go back one page? These are all the heat engines that we're going to talk about in this, and there are 4 of them. This one is the external combustion machine, which is like a steam engine, like a steam locomotive. This one is a steam turbine. This one is a gasoline motor, just like in your car, unless you have an electric motor. And this one is called a Stirling engine. Okay, so I'm not going to go through all of these slides, but this one's very nice. It tells us how steam engines work, and it takes 2 minutes and 53 seconds. This one is the footage farm, which is the old one, that the old school one, which it's only about a minute and 20 seconds. And this is the idea we already talked about with how a steam engine works. So I won't go over this again. This next one is a gasoline combustion engine, and once again, this is about 2 minutes long, and it describes how a gasoline combustion engine works from the footage farm. And it's queued right up for you. This one's really interesting. It's 8 minutes and 30 seconds long, though. And this guy, I think he's got a website called Smarter Every Day or something like that. But he goes to a shop where they have put a plexiglass cover on a lawnmower engine, so you can actually see the lawnmower engine firing. But the idea here is that you're going to draw in a fuel-air mixture, and that will represent the hot heat, the high side. The fuel-air mixture is going to be ignited with a spark, and it is going to explode. And when it explodes, it causes the internal energy of the system to push the piston down. The piston is connected to your flywheel, which allows you to do work. It runs your lawnmower or something like that, and that's the work that you do. After it goes down one time, it goes back up and it pushes the exhaust out the valve on the other side. And so this is the exhaust valve, and the exhaust goes out. Now it still has enough speed so that it pulls down, and when it pulls down, it will draw in or suck in air fuel mixture. Then it will go back up and compress it and spark. And once it sparks, it will explode. And so this is a 4-cycle engine because it has 4 up downs. And so the first one is called intake. So when it goes down, it intakes or pulls in the air fuel mixture. The second one is called compression, and where it presses up to the top. In the third one is called power. And so when it presses all the way to the top, it explodes the gas fuel mixture, which pushes down. That's the power stroke. And the fourth and final one, when it comes back up, is going to have the exhaust come out. So intake, compression, power, exhaust. Intake, compression, power, exhaust. And you'll be able to see that happen in either of those 2 videos. So once again, what we're looking at is the ability for heat to cause a change in internal energy, which allows us to do work. How much work? How much work depends on the difference between the hot side and the cold side. Okay, the next one is called the Stirling engine, and this is a marvelous one because it really doesn't require any like high heat. So one of the problems is that the guy that made this, his name was, what was it, James Stirling? He was actually a minister, but also a scientist, and a lot of the people in his church were working in factories, and the factories were dangerous because they had these high pressure steam engines that were making the factories work saw blades and that kind of thing. But the problem is those early steam engines would sometimes blow up. And so he made a low heat version of an engine called the Stirling engine, which is just brilliant. But it basically, this is a cup of hot water that I put in the microwave, and it just can work with a cup of hot water. So it's actually pretty amazing. Let's take it out, take a look real quick. 10-second video here. So yeah, that's really pretty simple machine. But I did cheap. I put an ice cube on top because what we want is we want this heat source below, and we want the top to be cold. And so the greater the difference between the hot side and the cold side, the greater the change in internal energy and the greater amount of the work that we can do. And so the way this works basically is that you have what's called a displacer, which is pretty much just a piece of foam that moves up and down. And what it does is it covers the cold side, and then it covers the hot side intermittently. So when it covers the cold side, the hot side is exposed, and when the hot side is exposed, the air inside expands and pushes up on the piston, and then the displacer moves up and covers the displacer moves down and covers the hot side, and then the cold side is exposed, and then the cold air contracts, and so the piston goes down. And so this is just basically a two-cycle engine. It just has the hot side exposed and expands, and then it has the cold side exposed and it contracts and expands and contracts, and expands and contracts, and expands and contracts. And it does it with very, very low pressure. It's not dangerous at all. Um, anyways, that's called the Stirling engine, and I'll probably show you that in action in class. And then, do I have any more? Oh, this is the steam engine. We already kind of talked about the steam engine, but steam engines are really super important because most of your energy is created by steam engines. You may think that steam engines are gone, but steam engines are not gone, not at all. Almost all the electricity that's made by heat, burning coal, burning gas, burning methane, burning garbage, and even nuclear. They all run on steam turbines. And so here we got a nuclear system where there's nuclear pellets, like uranium pellets, heating up water. This water gets so hot that it causes steam. The steam goes through a turbine system, which spins a generator, which sends electricity to the city, and then it cools down and it cycles around again. So just another version of an engine. A couple more things maybe to end off with. We got the summary here. And so the summary, heat added to a system, Q, will raise the internal energy, U, and allow it to do useful work, W. This means as long as we have a source of heat, we can get an engine to do useful work for us, usually either by pushing a piston or spinning a turbine. Number 3, the amount of work, W, it can do depends on the difference between the source, QH, and the sink, QL, which is the low side, the sink. Number 4, the external combustion steam engine, internal combustion gasoline engine, steam turbine, and Stirling engines are all heat engines, which all do work based upon the laws of thermodynamics. Couple more things. There's a cute little a YouTube playlist of all sorts of amazing, like, old school machines. This one is a windmill. If you've ever wanted to see a Dutch windmill sawing wood just using the power of wind, that's awesome. There's also a historic sawmill, which I'm going to make that into an ed puzzle for you to do. The sawmill actually runs on steam power, and so that's using the steam engine just like we have today, a steam turbine, just like our Fleischmann, our miniature toy steam engine in class. What else did I want to show you? So the last thing to do is to draw yourself a picture of one of the 4 types of steam engines or heat engines, and then do a one-pager which basically describes the 2 laws of thermodynamics, which I've summarized, of course, here. But they all follow the same idea, right? The idea is simply this. First law of thermodynamics says that we have some source of heat which is going to cause a change in internal energy, which allows us to do work. And then how much work? Well, that depends on the difference between the source and the sink, the QH and the QL. Everyone's the same way. They have a source of heat energy, which raises the internal energy, which allows us to do work. How much work? Well, that depends on the difference between the QH and the QL, the source and the sink. And we could say the same thing is true for any of those. And so that will be a test question, kind of like in the essay format. Can you explain the first and second laws of thermodynamics with respect to heat engines? And this summary would work nicely if you were trying to do that. Okay, and now we're really done. So I will see y'all later.